All right, good morning, good afternoon, everyone. Welcome to the hottest seminar. Today we have two talks, the first of which is by Colin Zwanziger on Hofmann-Streicher universes via coalgebra. So Colin, take it away.
Okay, yeah, thank you, Emily. So I'm talking today about generalization of the usual universe and models of presheaves, which is also often known as the Hofmann-Streicher universe in presheaves. So throughout the talk, I'm going to assume in the background that we have a Grothendieck universe, which you can also think of as a full subcategory of sets. And I thought that I might situate us by going back over the Hofmann-Streicher universe itself. So this is kind of a recap of the Hofmann-Streicher paper from 1997. I guess cast in my terms a little bit. So the idea is that if you have this Grothendieck universe, then if you have a category C, which is small for that Grothendieck universe, you can look at the category of presheaves, and we can actually enhance that category into a full-blown model of dependent type theory. And what I mean by model of dependent type theory is basically a full split comprehension category, although I'm going to use the index category perspective rather than the fibration perspective. So I'm going to talk about having an index category of types. What that means is that for at any presheaf, we're going to have a corresponding category, which is the category of types, so to speak, in the context of that presheaf. What that will be is, given the presheaf P, the category of types in context P will be the U small presheafs on the category of elements of P. And the reason why that's a good idea is that leads to this natural type comprehension. So if we have one of these U small presheaves on the category of elements of P, then we can include it into I guess not U small but still small presheaves on the category of elements of P, and then that's equivalent to the slice of presheaves over P. And so that gives us a way of going from one of these U small presheaves to a map into P. So that gives us our comprehension of types. So far we've just defined the model of type, the sort of natural model of type theory in set to the COP. So what we really want is a universe in that model of type theory. And so what I'm going to mean by universe, I'll actually call a universe a type classifier. And what I mean by that is a category internal to the category of context of the model, such that the externalization of that internal category is isomorphic to the index category of types. And so more concretely, what I'm looking for in this category model of presheaves is an internal category in set to the COP, such that for any presheaf P, the category of internal functors from P viewed as a discrete internal category to this type classifier upsilon is isomorphic to the types at P. And then this should be natural in P. Okay, so something kind of cool about the argument that constructing the Hofmann-Streicher universe is that you can derive an expression for the Hofmann-Streicher universe just by assuming that it exists. So that's what we're going to do. So we're looking for this upsilon, which is going to be an internal category in presheaves. But internal categories in presheaves are essentially the same as presheaves of categories. And somehow it's easier to think about presheaves of categories than it is to think about internal categories, I would say. So I'm going to abuse the notation slightly and go back and forth between thinking of upsilon as an internal category in presheaves and a presheaf of categories. And so we want to get an expression for upsilon, viewing it as a presheaf of categories. So for each object I and C, upsilon of I should be a category. And by the cat-enriched unit lemma, we know that upsilon of I is going to be isomorphic to natural transformations from uneta of I to upsilon. And then we can reconstrue uneta upsilon and uneta I and upsilon as being internal categories in presheaves. So that's just what this step is. And then we want upsilon to have this property of being a type classifier. And so maps into it are equivalent to types. And so this expression is going to be isomorphic to types at uneta of I, which by definition is just U small presheaves on the category of elements of uneta of I, which when you think about it, you wind up realizing that this category of elements is just the slice of C over I. So then we get that upsilon of I must be U small presheaves on the slice of C over I. So in the end, we just define the Hofmann-Streicher universe to be this, and then that turns out to work because that defines a presheaf of categories. So far so good, but we may want to think about generalizations of the model of presheaves and its Hofmann-Streicher universe in different directions. And one natural direction to think about would be to go from presheaves to sheaves. And this turns out to be a little bit problematic, which is kind of interesting. So we can kind of get started doing the same thing again. And so given a U small site, we can look at the category of sheaves on that site, and then we can think about enhancing that into a model of type theory. And so now for any sheaf, we define the types in the context of that sheaf to be sheaves on the U small sheaves on the category of elements of that sheaf, with a coverage, which is kind of an interesting coverage because we're talking about covers in the category of elements. So that will be actually a family of elements. And so what we take to be a covering family of elements over an element, it's actually a matching family whose amalgamation is that element. And then there's a natural comprehension for this notion of type, similar to the presheaf case. And so again, we want an internal category which externalizes to the index category of types, which we call a type classifier. Okay, so we can set about doing the same thing again. So we're looking for an internal category, upsilon, in sheaves, but we can include those into internal categories presheaves, which we have seen are the same as, or essentially the same as presheaves of categories. So we're again looking for a certain presheaf of categories. And we can derive what that should be if it exists. So we can say, well, at each object I, upsilon of I, just by the Uneta lemma, is going to be natural transformations from Uneta I to upsilon, which we can reconstrue as internal functors from Uneta I to upsilon. And then we have this adjunction between the inclusion of sheaves into presheaves and the sheafification. And so we can transpose in the adjunction. So we can go from internal functors from Uneta of I to upsilon to internal functors in sheaves from the sheafification of Uneta I to upsilon. And then because we want this upsilon to be a type classifier, then we get that this is isomorphic to types over the sheafification of Uneta of I, which by definition is U small sheaves on the category of elements of sheafification of Uneta I. So we can try setting, we can try defining our upsilon like this. But there's actually a little bit of a problem here because, well, we derived what this thing had to be from its existence, but we actually don't know that this defines a sheaf. We just have something that's like a presheaf of categories here. And it actually may not be a sheaf in general, or it is not a sheaf in general. And it may only be a stack, which is to say that if you have a matching family, then the amalgamation is only unique up to isomorphism. And so a counterexample to having a sheaf was already noted in like 1960. And so in particular, you can just look at the case of sheaves on a topological space, or U small sheaves on a sheaves on a U small topological space. And in that case, the expression for upsilon actually simplifies because in sheaves on a topological space, the representable presheaves are sheaves, and so they're isomorphic to their sheafification. So we can simplify out the sheafification, or we can remove the sheafification from the expression. And so in the end, we simplify down to upsilon at an open set U is just U small sheaves on U. And so if you think about this presheaf of categories on the opens of a topological space, taking an open set to U small sheaves, then you can observe that's a stack in general, not a sheaf. And so that's a little bit problematic because basically we've seen that sheaves on a site doesn't have a type classifier in general in the sense indicated. Of course, there are a number of ways around this, so to speak, that have been looked at. So for instance, you could just bite the bullet and say, well, okay, I guess I'm going to work with stacks instead of sheaves, for instance. So what I want to talk about for the rest of the talk is a different generalization of the model of presheaves and the Hofmann-Streicher universe in it, which is it's an a priori a different direction than this generalization to sheaves. But it turns out in the end that in many cases you can use this construction to replace a model of sheaves by one that's categorically equivalent, but which has a type classifier, and where because it comes from this construction, it's a model which is built up in a nice way. Okay, so the idea, the direction of the generalization is coalgebra, and so obviously we're trying to axiomatize some facet of the model of presheaves. So I just wanted to give to tip my hand a little bit about what that is. And basically the idea is that we have this forgetful morphism of models from presheaves to families of sets over the set of objects of the category. And that forgetful morphism of models turns out to be strictly comonadic in a suitable sense. So that means that we can recover this model of presheaves as up to isomorphism as coalgebras for a comonad on families over the set of objects of the category. And so in general, when you have a comonadic functor, you can there are various theorems of the form. Well, if I have some structure in the codomain, then I can use that to build the same structure in the domain. In particular, when you have like a Cartesian category with a subobject classifier and a Cartesian comonad on it, then you can form the category of coalgebras, and you can construct a subobject in the category of coalgebras from the subobject classifier in the category that you started with, and so that's kind of what's you can use that to construct the subobject classifier in set to the C-op from the one in set to the objects of C, and we use a similar construction we're going to use a similar construction to construct a type classifier in set to the C-op from one in set to the objects of C. And of course, what is the type classifier in set to the objects of C? Well, it's just the constant family at the Grothendieck universe U. So you can sort of analyze the lifting of Grothendieck universes from sets to set to the C-op in Hofmann-Streicher's terminology as, I guess, being in two steps. One where you go from set to the objects of C, where the type object the type classifier is just the constant family at the Grothendieck universe, and then there's the step that goes from families over the objects of C to presheaves on C. Okay, so basically our as I said, our strategy is going to be to start with a comonad on a model of type theory, construct the model of coalgebra, so to speak, and then we'll lift the type classifier from the carrier model to the model of coalgebras. So if we start with a comonad box on a model-dependent type theory E. So again, I mean full split comprehension categories and comonad of full split comprehension categories in a suitable sense. So then one thing to note is that at any coalgebra, we have an induced comonad on E types at the underlying object of the coalgebra. And what that is that you take the type and then you apply the morphism of models to the type. So the morphism of models has a action on as an underlying functor and also has an action on types. So we apply the action on types, and then there's a reindexing along the structure map of the coalgebra. So that gives us a comonad indexed by the coalgebra. And the way we would construct this model of coalgebras is first we build the category of coalgebras for the underlying comonad, and then we need to make a presheaf of types on that. And so we take types in the context of a coalgebra to be the category of coalgebras for the comonad, which is indexed by that coalgebra. So that winds up giving us a model of type theory. And then just as a notation thing, I'm going to write U for the forgetful morphism from coalgebras to the underlying model, and then F for the co-free co-free morphism of models. Okay, and so then our theorem is that when you have one of these comonads of models and the underlying category is Cartesian, the underlying functor is Cartesian, then if you have a type classifier in E, then you have a type classifier in the coalgebras. And so basically, I mean, one thing you could think is that you just take the type classifier in E and then apply F to it, and then that gives you a category in the coalgebras. But that's actually not quite right. What you want to do is you find a certain internal comonad on F applied to the type classifier of E, and then you take coalgebras for that. So you hit the type classifier in the base with F, and then there's a comonad on that, and then you take coalgebras for that. So you're taking coalgebras for an internal comonad in the model of coalgebras, and that gives you the type classifier. And so basically the idea is we have this this indexed comonad, which is indexed by coalgebras, and that indexed comonad internalizes to this comonad on F applied to the type classifier of E, and then we define the type classifier in the coalgebras to be the object of coalgebras for that comonad. And then just to sort of concretely think about what that construction outputs, we can return to the presheaf example, and so we can get the comonad on set to the objects of C as somehow the induced being induced from the inclusion of the objects into the category itself. And then if you look at what the construction does, so our co-free morphism is this I lower star, and so we should build the Hofmann-Streicher universe as being comonadic over I lower star applied to the type classifier in families over the underlying objects of C, and that turns out to be just families over the set of morphisms into I. So yeah. So we don't get the Hofmann-Streicher universe just by applying the I star, but somehow we get the Hofmann-Streicher universe as comonadic over that. And you can do a similar construction to get a universe in sheaves on the topological space. So the continuous inclusion function from the underlying set of elements of the topological space into the topological space induces a kind of a geometric morphism or a junction of models from sheaves on the underlying set of points to sheaves on the space. And sheaves on the underlying set of points are equivalent to families over the underlying set of points. So that gives you kind of a comonad on set to the underlying set of points. And so if you take coalgebras for that comonad, then you wind up with this equivalent model, which has a type classifier or Hofmann-Streicher universe in it. And then you can generalize that even further to sheaves with sheaf models with enough points. But I should wrap up. So thanks for your attention.
Great. Thank you, Colin. I guess we're supposed to silently applaud. Any quick questions?
I have one.
Please.
If we do it to the subobject classifier, does it give the known construction of the subobject classifier as a universe of propositions?
Yeah. So the construction of the subobject classifier in the category of coalgebras, it's analogous. So you apply the co-free functor to the subobject classifier, and then you find a canonical comonad on that, and then you take coalgebras, internal coalgebras for that. Yep. And so this is the same construction, just sort of untruncated.
Good, thanks.
Okay, let's thank Colin again.
Yeah, thank you.